a semantic feature of interest is going to dominate the geometry of your data, that the points that end up nearby under some metric are going to be better modeled together than points that were far apart, and so on. Basically just projecting your hopes onto these clusters when really sometimes a cluster is just a cluster. Now, I mean, all this having been said, there are good reasons to want to break your data up into pieces sometimes. So for example, there are certain subpopulations and certain risk factors for certain kinds of cancer that, although they're significant on that subpopulation, are not predictive in the overall population. So if you could find these subpopulations and these risk factors, you could do a better job predicting who's going to develop this kind of cancer. Okay? So it's useful to find these kinds of small segments and simple models where things work out. And so this is the use for things like clustering that we're going to take seriously and try to solve in their own right. Okay? So in some sense, the idea here is we're going to use this model fit, this ability to make predictions as a kind of training signal for finding one good segment of the data. Okay? So a little more precisely, I'm going to work with sparse regression. Okay? So here, there's some real valued attribute z I want to predict using some other real valued attributes y. Okay? And I want to find an S-sparse linear rule for some constant s. So that's means my coefficient vector in this linear form has s non-zero entries. And so together with searching for this coefficient vector for the regression, I want to find some kind of a Boolean condition on, say, some other set of Boolean variables x, so that in that conditional distribution, this sparse rule A on y predicts z. Okay? And in this work, the conditions will be k DNFs for some constant k for a reason that I'll get to in a couple minutes. So the main result here is that if I'm measuring the error by the soup norm, I can do this really well. So if D is an arbitrary distribution over these Boolean attributes, the x's, the real valued attributes that I'm going to use to make my prediction, the y's, and some designated target real valued attribute z, okay? If there actually was a KDNFC and some sparse coefficient vector a, so that in the conditional distribution on c being true, z is always within epsilon of this linear form a on y, right? So that's epsilon soup norm. And if c also occupied a mu fraction of the distribution d, then I have this algorithm, it runs in polynomial time, takes examples just drawn from d, and so with probability 1 minus delta over the data, I find some other S sparse A prime and some other KDNF C prime, so that in that conditional distribution, condition on C prime, this linear form A on Y has at most epsilon error at predicting Z with probability 1 minus gamma, and C prime picks up at least a 1 minus gamma fraction of mu. Gamma is some controllable parameter here that, say, is dictating my sample complexity and running time. Okay, kind of what you would expect. And I only want to say a couple words about how this is actually done. The idea is I first solve this list regression problem. What is that? Well, okay, so I have my training set of m examples, and I find a polynomial size list of candidate regression coefficients, right, that in particular includes in it the optimal soup norm fit A prime on this unknown subset of my training set where that unknown condition C was actually satisfied. Okay? It turns out that using the fact that this is a soup norm and I have constant sparsity, this is not hard to do. And then what I'm doing is I'm going to use whether or not I had error greater than epsilon on a given data point as a label for using this candidate coefficient vector. And then using those labels, learn some KDNF C prime corresponding to the candidate coefficient vector A prime. And I just pick the C prime that picks up the largest fraction of the data. Okay. So roughly that's how the algorithm works. Let me get back to the question of why KDNFs are sort of the thing of choice here. So basically, if I could solve this task, this, forgetting about sparsity even, just any variant of this conditional linear regression task, where the conditions could express arbitrary conjunctions, okay, then I would get a randomized polynomial time algorithm for pack learning DNF in this distribution-free setting. So this was the sort of the central open problem in Valiant's 1884 paper. It seems kind of hard. And so also this past year, Daniele and Charles Schwartz gave some new evidence basically showing that the problem is actually hard under a mild strengthening of Feige's random k-sat hypothesis. Okay, right, so, seems hard. And basically any natural kind of representation you would use here, except for KDNFs and parodies, can express conjunctions. Parodies don't seem that natural in this context, so KDNFs are it. Right. Now, the other limitation of this work was that we're talking about sup norm, and that's nobody's favorite norm. Okay, so it's very natural to ask, well, what about squared error? If I'm told that there's some regression fit that achieves epsilon squared error, what can I do? And one thing I can show here is that if I could find some other set of coefficients for regression that only blows up the error by some polynomial in n amount, where n was the number of Boolean attributes that I had for the x's, right? Then this will solve another problem that I'm calling agnostic conditional distribution search with a similar blow up in the error. What is that problem? Very, very briefly. Instead of all these real valued attributes, the y's and z's, I just have Boolean labels on my points. Okay, and I'm told that there was some good condition C star that makes the labels come up true a 1 minus epsilon fraction of the time, where C star occupies a new fraction of the distribution. Then my objective is to find some other condition C that makes the labels come true a 1 minus epsilon prime fraction of the time and occupies a mu prime fraction of the data. Okay, and so what this is saying is, if I could achieve blow up of this polynomial in n in the expected error for my regression task, I could solve this conditional distribution search task where this epsilon prime here is that same polynomial times the original epsilon. Okay. Why do I care about this? Well, so this is another problem that we've been working on, and sort of the best we know how to do for this problem, when you're talking about C being a KDNF, blows up the error by this O tilde square root n to the k factor. So this is going to be some kind of a bottleneck in getting low error for the squared error or whatever LP error regression problem, right? But we have a preliminary algorithm in this direction. So now let's suppose that my real valued points all have bounded 2 norm, and likewise the coefficient vector is bounded 2 norm. Let me suppose additionally that I have this factor 2 estimate on the target probability of that condition. I could find this with binary search. Okay. Then as a very, very simple algorithm that finds this O of n to the k approximation in the error under the 2 norm, which is kind of we're prepared to accept, and also only recovers an n to the k fraction of the probability, which is pretty disappointing. Okay, so the main open problem, or the first open problem that comes to mind here is, can I get rid of this n to the k loss in the fraction of the probability that I pick up for either this L2 error regression or dense regression, right? Not exploiting this constant sparsity. A related problem is, instead of assuming like actual constant, L0 sparsity, could we make use of the L1 norm of the coefficient vector, right? So that's sort of the way sparsity is typically handled. It's a little more flexible. Okay. Another natural open problem is, I said that my bottleneck was solving this conditional distribution search problem, but I was only blowing up the error by a square root of n to the k factor there. Can I match that? And finally, generalizing this problem from talking about regression on the conditional distribution, could I do other kinds of supervised learning tasks, like learning a half space? Okay, that's all.
I'd like to thank all the speakers for this session.